So he goes for actually a pyramidal structure. Why a pyramid, right, will become obvious, a pyramidal structure. And as I said, right, I mean, why, so earlier, right, when we talked about a pyramid, right, I said that a pyramid is useful under certain conditions. What was that? When did we say that a pyramid is useful? The pyramid you understand, right? So what we are saying is you have at a certain, this one, okay, resolution, then you downsample, and you downsample, then you downsample. If you do that, I said that there are certain advantages to kind of having a pyramid like that. Can somebody recollect? One of the advantages that I mentioned at the time is if you wanted to sort of what do you call, if you wanted to align two images and if you wanted to find out what is the underlying transformation, then it's easy to sort of work at a lower resolution, get a good initial estimate, use that to start the, if you're doing it iteratively, use that to start the next thing, and then right, it will help you to kind of say converge fast and in a more stable way than sort of searching everything at a high resolution. That's typically the reason why, let's say, people go for, you know, this one, a pyramid. Okay. Now here the idea is that a pyramid by which he calls each one as an octave now. Octave is like what? I mean, either you go up by 2 or you know, or you go down by half, right? That's when you say that you're moving by octaves. So what he does is the following, right? So he says, so what he does is, so for example, if we still go back to what we had, so we had sigma, k sigma, right, all the way up to what is it? We had something like k power 4 sigma. Huh? We had this, right? Now this, call this as octave 1. Okay, which is at the highest spatial resolution. Now, see somewhere here, right, we would have had a k square sigma, no, k square sigma, then we have a k cube sigma. So the k square sigma is actually 2 sigma, right? So what he does is he creates another octave, which is called as octave 2, and in octave 2, right, what you will do is this you see 2 sigma that you had, no, this is actually an image here which is actually blurred by, you know, blurred by 2 sigma. So this 2 sigma blurred image is actually downsampled. Downsampled means just decrease its size by half along both dimensions, and then at this decreased size you again right, I mean, you know, so for example you have something like, you see, k square sigma here, right? So k square sigma is like, you know, 2 sigma, right? So you start with 2 sigma, then the next one is again 2 root 2 sigma, goes up like that. So you can think of the next guy here downsampled, and then you have another bunch of images sitting in that octave. I mean the reason, right, why something like this is done is because instead of scanning structures at one resolution and trying to find out, right, where I can get my structure, instead of that, if you have a 2 sigma blur and if you have downsampled the image, right, then it means that, then it, right, effectively means that a large structure, right, could still be captured even at a lower sigma, right, at 2 sigma, because you have downsampled image, a bigger structure would now become smaller, and even with, instead of going up to 4 sigma, even at 2 sigma, right, you might be able to you know, trap that structure, right, you might be able to kind of catch that structure, right. So that's the reason why. So instead of working at one resolution and going through all the scales, it makes a lot more sense to actually downsample an image. And of course, the aliasing you don't have to worry, because this blurring and downsampling is actually a good thing to do, right? Like I said, this directly downsampling is not a good idea. That I think we discussed, right, at one point of time. So that is anyway happening here, because we blurred it with some Gaussian, which is at 2 sigma, and we are downsampling it, and then so the next octave starts from the 2 sigma from the earlier octave, but then that 2 sigma downsampled, and then it goes on. Then if you want one more octave, you can add, and so on. So he shows that, right, using this, I mean, you don't miss things. Otherwise, you would have to computationally do a lot more in order to ensure that you get most of the features. And there's no way to write. There is no way to verify this. Okay, there's no way that there's nothing like a ground truth, right, where we can say that, right, these many features I have to get, and then which algorithm gives me that, right? We can think of that. No, in an image, right? It just, like I said, it just fires wherever it feels, right? Things are, there is a good activity of a foreground with respect to its background. I mean, that's the way you have to see, right? An activity that is significant enough at a region as compared to what is around it. Okay, whenever that happens, it's interesting. Okay, that is loosely the interest point, and each one could have it in right, in their own ways. And this paper builds it up like this. Okay. Now comes the point as to the
Got the structure, but how do we match it with the original structure?
okay. Oh, you are saying how do I come back and locate where it is? Well, because you sampled it by that factor, no? So you know. So
Just come back.
you just have to come back. Yeah, so right, so which is also the reason why for example, right, when you are coming back, right, you still have to do some subpixel accuracy alignment and all you should do. Otherwise, it should not happen that when you expand it, right, you lose out in terms of the spatial accuracy. That's why they don't go too many octaves. It's not like you have octave 3, 4, 5 and all. They don't go too many because when you come back, right, your location could be in trouble.
Yes, that's what
Yeah. So I think they just go like, I think it's just octave 1 and octave 2. I don't think there's too many octaves there. Max, I think it's only octave 3 or something, not more than that. Yeah, that's a valid question. Then, okay. So one of the things, right? So key point, right, as he calls it, or we might want to call it an interest point. So the key point, right? It defines the key point through something. Okay, what he calls through a dominant orientation. Okay. Huh.
So instead of octave 2, in octave 1 itself, we can go to higher sigma, but because of the computational efficiency, we are going down.
Correct.
That is the only reason.
That is the only reason. Yeah, that is the only reason. So this dominant orientation, so it's like this, right? So what we want to do is, if I have an image, and if I apply my SIFT, right, this algorithm, then I want to be able to tell that I have a feature here, I have a feature here, I have a feature here, whatever, right? I have a bunch of features, each is a SIFT feature, but in addition to that, right, I also kind of want to be able to say something more about it. Okay, when I even show that feature. Okay, and that is called an attribute of that feature. A descriptor is something else. Okay, a descriptor will right, a descriptor is something that we will use eventually for actually matching and so on. But to even to do to be able to define a key point just by the extrema, right, he does not define a key point. Okay, now because all of this is kind of spread out, right? I mean, it's not easy to catch them all under one roof. So I'll just indicate what those steps are. So first of all, a thresholding is done on the extrema, right? So that it's something which is just an incidental extrema, right, is not taken into account. A thresholding is done on the log or dog extrema. Okay, that means only the things that cross a certain value, right, will even be kind of considered. And then a unique orientation is assigned and it turns out that you can have, okay, I think it's assigned to each extrema or key point or to each interest point. So how this is done is, right, so around the local extrema, so if you have found a local extrema, right, around the local extrema, what you do is, okay, this I will write down. Okay, so around the local extrema, a suitable window is chosen. This can be 16 cross 16, something like that is chosen. Again, there are some hyperparameters, and in fact, this, strictly speaking, this window in fact depends on the sigma, the scale at which you are, and so on. But anyway, let's not go too fine into the implementation issues. Just want to understand, right, what is going on. And the histogram, yeah, this is what is important. Of 36 bins, each bin of 10 degrees, each bin of 10 degrees is computed using the points around the extrema. What does this mean? The points, I will first write this, then I will tell you what it means. Of course, it's fairly self-explanatory, but well, anyway. So what this means is that, like for example, right, you have a kind of, right, just an orientation, So, you have a theta going from 0, 10, 20 degrees all the way up to say 360 degrees. So, you got that many bins, and the idea is that right, when you actually look around this local extrema, this is your local extrema. No, actually, right, this is for knowing the dominant orientation of that point, so that right, when it appears in another image, right, you should know how that orientation is, so that you know the kind of relative orientation between the two, and that helps you to solve for these rotational ambiguities. Oh, that's what I'm saying, right? These are like, you could have considered 72 for all you care, right? Yeah. Well, in fact, some papers I've seen, they write like 24 or something, which could be a 15-degree interval, right? Some people say 15. That's an implementation issue. That's what I'm saying. Let's not worry too much about Y36. Yeah. How? Okay. If you're asking Y36, that's for computational purpose. And maybe it will still work if you have C24, just a matter of coarser theta, that's all. But I'm saying more important than that is the idea behind what this bin is trying to capture. What this bin is trying to capture is, for example, right, I mean, at each point you know to compute the gradient magnitude and the orientation, right? If you have an edge pixel, we know how to calculate using a local neighborhood around it. We know how to find out. I mean, you know that, right? I mean, you just have to do tan inverse gy by gx, that will give you the theta, and then magnitude is like gx square plus gy square, whatever, right? So, both you can do. So, what is done is, so if you find a certain angle, right, and if you find a certain gradient strength, right, you kind of drop it into that bin. Okay, and then another point, right, you might find a different orientation, different strength. But what you're dropping in each of those bins is the strength of that this one, right? So, it is the gradient, strength of the gradient, right? So, you're plotting. So, what you're plotting is the strength of the gradient with respect to the orientation. And what you do is, the one bin that gets the maximum maximum strength, right, that is what you kind of tell is the kind of dominant orientation of that extrema. So, it means that right around it, right, many of them are kind of aligned in a certain way, right. So, that you want to say that it's like, what to say, I mean, it's like saying that if you had a local structure, right, if you had an arc or something, right, then maybe it has a certain orientation, right, or it's a line segment or something whose orientation you try to capture. So, when you say that extrema has a dominant, see, the extrema itself will have its own orientation, right, but the dominant orientation is coming from examining what is around it and trying to find out what are the strength of the gradients of those pixels, but what orientation are they, and then once you kind of put them all into this sort of histogram, then you get one bin, right, that will have the maximum this one. Are you guys following this? So, the gradient, right, so maximum gradient will appear in some bin, and that we declare to be the dominant orientation of that key point. This is okay. Right. So, you have something like it's a dominant orientation. So, just to finish this, right. So, the bin with highest peak. So, the bin with highest peak, or the highest gradient norm or whatever, or the highest gradient strength. Strength is chosen as they say, a reference orientation. As a reference orientation for that key point. For that key point, that means for that extrema. And in fact, one more thing that they do is, any bin, okay, with, these are all, again, this is all actually very fine implementation issue, but I thought this is a little more interesting, so I thought I'll anyway write greater than 0.8 peak is also considered a possible orientation. Okay, so, what this means is that at that point, right, when you show this, so for example, right, so okay, so if I come back to this figure, so what will happen is, right, so when they want to show a SIFT, sometimes, right, you find actually you may find actually two arrows, I mean, one like this and then another like that. Okay, if you are wondering what those two arrows mean, what it means is that there are actually two possible orientations perhaps, right, and one is then the strength of that norm, the gradient norm is what is the length of that arrow, and the orientation is whatever is this orientation, right. So, anything that is above 0.8 peak, right, they kind of suspect that, you know, the thing is that when you are trying to match it with another, okay, when the same image appears under, let's say, you know, a different orientation, and also at that time when you try to create a match. So, if there is multiple match possible, right, like for example, one of them, even if one of them, if with respect to, well, one of these key points, if you are able to match, it's like at the key point you have got, you know, two options, right, when you know, either of them could actually work when you do the matching. So, this is to make sure that you don't miss things, because you're right, eventually when you go to stereo and all, right, this will come very handy. Right? Why are we doing this? Because when we go to a geometry, right, geometry is all about picking points, because if you have plain image, there is no geometry that you can make any sense of, right. I mean, if I give you a plain image, what geometry can you even talk about in there, right. So, geometry comes because there is a lot of activity in the image, and there whenever you want to find out structure, when you want to find shape of an object, right, all these points you have to find, right, what those points are, where did it go in the other image, where should I look for it. So, at all those places, right, this will come, and the more robust matches you have, the better you have a sense of the scene, right. I mean, if I have 1,000 points that I can match, that gives me a much better sense of what I am looking at than, let's say, having 100 points, right. So, the idea is that these are all kind of what do you say, you know, this one, enablers. So, these are like enablers to get the match going. Okay. So, which is also the reason why you could have, so a key point, right. So, you will typically find it as some x, y, what is it, sigma, and then actually a theta, and then theta can also be theta 1, theta 2. Okay. Then comes a description, right. This is only to say that I have these many key points and these are all to be matched, right, and then some of them could surface in the other image, some of them may not surface also. Okay. Sometimes because of occlusions, right, you don't even see them. So, all of that can happen. My idea is that I have got an image right here, and I have got to say another image of that scene. Okay, and I want to be able to right. Suppose I have got these, you know, SIFT points that I've got here, and I've got some SIFT points here, and then I want to be able to find a match, right. I should be able to say, right, that this SIFT point is this. I should be able to say, right, that SIFT point is that, and so on. And in general, right, and we don't want to make. You can of course, you know, make this match itself elegant if you knew a little bit more about the underlying scene. For example, if you knew at what angle this was taken, these two images were taken, then maybe that simplifies, that will sort of automatically constrain where this guy could have gone, right. But in general, right, if you don't want to assume anything, and if you still want to do a match within a reasonable search region, right, and not really constraining it to a line or something like that, which you can if you knew a little bit more about what's going on. So, if you just wanted to search within a local space, right, you want to be able to have a descriptor, right. So, what you need is actually a feature, this one, a descriptor. And again, the subpixel accuracy and all that is there, right. I don't want to repeat all that. Okay, whatever we did in Harris corner detector, right, something similar also happens here. You have to get down to the subpixel accuracy of the extrema and all. Okay, I'm not going to repeat all that. We have already done that, so you can just read it up. You'll easily follow that now. Having done that once, we don't want to keep repeating. Okay, now the SIFT, this one, a descriptor, is a 128 cross 1 vector, dimensional vector, is a one terminal, and which is derived as follows. Okay. Now, do we have? Okay, I think I can finish this. Okay, now what do you do? So, you take a 16 cross 16 area or grid, area is chosen. So, it is like this, right. So, now you have the interest point, right, and the say reference orientation is something which you want to store in any case. Okay, the dominant orientation which we found. Now, what we are saying is we have this interest point, and around that, right, we will. So, these steps are very similar to what we did just now, but there is some changes. Is chosen and the gradient norm and orientation. Of course, some of these things if you have already done for when you actually defined the key point, you could use that information. You don't have to recompute. Are found for each pixel. For each pixel. Then their angles are recomputed. So what this means is that you have these angles, right? Now these angles are recomputed. I mean, when you do this, right, you will get the orientation, right? So these angles are recomputed with respect to the dominant orientation. That means relative to the extremum point where these are, with respect to this dominant orientation. Or what is called or using the reference angle. I think this is a different wording. Using a reference angle, using the reference angle for that key point for the SIFT, using the reference angle of the SIFT feature point.
So that will basically be like a difference between the normal orientation and the orientation of the key point.
No, sorry. What say it again? Difference between the
Gradient angle and the orientation of the key point.
not at the key point, right? So what we are saying is we were trying to find out around the key point with respect to the key point, where are the others? This is like, see, you are finding the gradient norm and orientation are found for each pixel, right? That means around the extrema. And for the extrema itself, right, you have like a kind of a dominant orientation which you have assigned it. So now what you are saying is with reference. So for example, if you have an absolute angle, see, typically when you compute an angle, it will be with respect to the x-axis, right? Instead of computing with respect to the x-axis, if you have a dominant orientation, with respect to the dominant orientation, where are these other points, where their angle is with respect to that?
So like, are you computing the angle of the point or the
Point of these points.
Okay, so how will you store it?
We will see that. Okay.
So you are calculating the angle between the orientation and the point where
Yeah.
gradient is calculated.
We are trying to see, for example, what you are saying is you are taking a neighborhood, right, around the extrema. You have already found a dominant orientation for the extrema. That means this whole sort of local surface, right, has a certain orientation. And what you are saying is the points, when you compute the orientation for all the other points, that will have a reference direction which is your x-axis. Instead of that, you are trying to find out with respect to this key point, where are they oriented? The reason being that if, let's say, if in the second image, right, if the whole thing. Okay, so I think we have run out of time, right? We'll just continue in the next class. Okay.